So this is the second mass spec video. The first one is called Mass Spec Basics. This will be Mass Spec Examples. So I'm going to use these various examples of mass spectrometry scans to show what we can learn from them. This molecule is methane, CH4. And if you run this through a mass spec, it'll ionize, become CH4+, and it will show up in the mass spec with this parent peak here of 16 units. Well, it's a carbon, 12 units, and 4 hydrogens. Its mass is 16. So this parent peak here gives us that mass. Now, you also see peaks here at 1 unit less each time. This is missing one, missing another, missing another, missing another, and you don't see anything else below that. Okay. If you were trying to figure out what this peak was from, it'd be having one less mass unit. There it goes. One of the fragments broke off. Let's go back to here. Now, this is kind of a boring one, so let's get a little bit more interesting. This is butane, and it's a larger molecule. And way out here, we have a peak at 58. This is our parent peak. And it's our parent peak, and you see it's not very tall. A lot of this over here is going on. But this is our parent peak at 58. And you're not going to see things substantially higher than the parent peak, 1 or 2 units, but we will see some examples. So butane has got 4 carbons, 4 times 12 is 48, it has 10 hydrogens, so it's 58. This is the parent peak. But what happens pretty easily for this molecule is it breaks into 2 chunks. And this peak here, which is at 43, is missing 15 units of mass, which is the CH3 group that came off. And that's pretty common as well. So again, fragmentation patterns. And then this one would be missing more of the molecule, etc. And looks pretty much like that. This one is now decane with 10 carbons. And way out here, you could see at 142, that's going to be 10 carbons, which is going to be 120 and 22 hydrogens. But that's pretty fragile, and it breaks up into chunks, and you start seeing each one of these evenly spaced little blobs is a shorter and shorter chain. This is not going to stay stable as a positive ion. Now here we've got something interesting, okay? This is bromobutane. So we've got 4 carbons and 4 carbons, yes, 9 hydrogens and a bromine. And we get 2 parent peaks, and these actually are both parent peaks. They're separated by 2 units, and one is just a little bit shorter than the other one. Same pattern is showing up over here. One's 2 units higher than the other, just a little bit shorter. But by the time you get over here, you don't have that doubling of the peak situation. Now back here, if you have a peak at 57, let's think of what that might be. That's going to be the 4 carbons, 48, and 9 hydrogens. That's your mass of 57, which is everything but the bromine. So this peak is everything but the bromine, and way out here we've got it with the bromine. And the reason there's 2 peaks, and this is super huge and important because it lets you identify bromine really easily, is because bromine has 2 isotopes. Bromine can be bromine 79, and it can be bromine 81. Bromine 81 has 2 extra neutrons. They don't matter chemically, but they do matter when it comes to its mass. So this peak here is when it's got the mass of 79, that mass unit. And this one where we've selected is at 136, I believe. And this one's at 138. So if you take that 136 and you take away the peak of 79, okay, you're 136, I probably should have subtracted that before, you're going to end up back here, minus that. And if you go to this peak here, this is the same molecule, only with the heavier isotope of the bromine in it. And again, the same kind of losing carbons pattern back there. Okay, so this is another pretty indicative pattern. So remember bromine, we have 2 parent peaks separated by 2 units, and the ratio is about 1 to 1. And there's another peak for the bromine, let's go back to that, which is missing that 79 or 81, because that can break off pretty easily. Now here we've got this other pattern, which is a chlorine pattern. And chlorine atoms, again, have isotopes. The isotopes can be 35 and they can be 37. And being 35 and 37 makes them 2 units apart. And they are found in a 3 to 1 ratio in nature. So you can see we got this 3 to 1 peak. It's not the same as the bromine, which is about 1 to 1. And so this is indicative of chlorine. Now, if you recall from periodic table, chlorine's average atomic mass is just about 35.5 because 3 out of 4 of them are 35s and 1 out of 4 of them is a 37. So here we've got that chlorine 35, and here we've got that chlorine 37. And then if you take your, and the masses were 78 and 80, if we take our 78 and take off the 35, we are going to be over here at 43, which is the big peak again, and that's going to be our 3 carbons, 36, and 7 hydrogens, 43. So we can figure out both that the atomic mass with the lighter isotope is 78, heavier isotope is 80. We can identify that there is a chlorine in there, and if we were getting really good, which we probably won't be, we could start looking at some of the patterns there. So here's another thing that's kind of indicative. In this one, the parent peak is at 59. On all of the other ones we've been looking, the parent peak has been at an even number. If you just have a hydrocarbon, you have an even number of hydrogens. And carbons can be whatever, but carbon's mass is 12, so you have an even number. If you had a chlorine of either isotope or a bromine of either isotope, they had odd masses, but they replaced a hydrogen, so we ended up with an even mass. But here we have an odd mass. And what this is indicative of is having nitrogen in the molecule. So here's our nitrogen. So there would have been a hydrogen here, so we're missing 1. We've got 2 coming back in. So just as in the degrees of unsaturation, we've picked up an extra hydrogen, 1 unit of mass. Nitrogen itself is 14 units of mass, but the extra hydrogen makes it odd. So if you find an odd mass, molecular mass, probably means you have a nitrogen in your molecule. This helps us to figure out the formula. Okay, I pushed my window too far over. This molecule here, now we're on screen, it's called isophthalic acid, and it's got all kinds of stuff going on here. The most important thing that's going on here is that we have this peak here, which is at 166. It's at 166. And I wanted you to notice that over here, we have the short little carbon peak that we talked about on the other video coming in. And whereas this peak had an intensity of 83 units, you can see that up there. And this one is down at about 7 units. So it's not 10% of it. And we don't have 10 carbons. We have 6, 7, 8 carbons. But that's one of the things you can tell by that ratio, is roughly how many carbons you have. Now, you can just barely on this spectrum see another peak right there. A little teeny one, even smaller than the one that's 1 mass unit higher. And that's actually that you could have 2 carbon 13s. 2 out of these 8 atoms could be carbon 13s. And of course, the odds of that are roughly 1/10 for the first one times roughly 1/10 for the second one. So you see this little teeny pipsqueaky peak over here. And here we have one more molecule here. And this one we have, there was one piece I wanted to show you about this one, is here we have our parent, this is the parent peak at 106. This is the isotope peak. So 106 is going to be the 7 carbons, which is going to give us 84. And then we have 6 hydrogens, which is going to give us, we're now at 90, and the 16 from the oxygen. So 106 gives us this peak here. And this is the isotope peak. But what's the deal with this peak here? It didn't really show up having 1 unit lost very often on the other spectra, but here it's almost as big as the parent peak. And the deal is that this aldehyde hydrogen here, it's actually really easy for that thing to break off. So the fragmentation is bye-bye hydrogen, and we go down a peak. Goes down 1 unit for the peak there. So the upshot summary of this is certain atoms are pretty easy to spot in a mass spec. Bromine with the 1-to-1 mass ratio and subtracting off the 79 or 81, getting a strong peak, that's pretty indicative. Chlorine with the 3-to-1 mass ratio parent peak, subtracting off 35 and 37 from the 2 peaks to get a strong peak, that's pretty indicative. Nitrogen having an odd molecular mass peak. Now, it's also possible, of course, to have 2 nitrogens, then it would be even again. And it's also possible to have 2 chlorines or 2 bromines, and those things do get a little bit more complicated. And with the fragmentation patterns, sometimes you have patterns that help you to get the structure. Mass spec is not usually used alone. It's usually used in conjunction with some of the other tools we're working with. NMR, which we've been working with, and infrared spectroscopy, which that'll be my next series of videos.